Hello world, my name is Anthony Bao and this is Trading Up. In Trading Up, you were given a list of trades that you can make and an amount of time that it costs to make each one, and you were asked to find the smallest amount of time you can trade given your starting item to a list of items that you want. We solved this problem using dynamic programming. We do this first by saying, suppose we already knew how to get from every item to every smaller set. So for instance, if our set here has size 9, suppose that we already had a table where we could look up how do I get from the item 1 to any set of size 5. If we already have all this information, then we can solve this problem relatively easily by saying, well, let's make a decision first about what trade to make. So suppose we had one trade that gives us 1 and 2. We make that trade, and suppose we also decide what output set we want. So suppose we choose 0 through 5 and 6 through 8 as our output sets. And then we just look up on our table, how much does this cost? Let's say it costs A. How much does this cost? Let's say it costs B. And then add it to the cost of this first trade. So the cost of this whole setup will be A plus B plus C. Then we just do this iterated over all possible decisions for this trade and all possible decisions for how to split up the output, and then take the minimum of all of them. And that will give us the least cost to get from our starting item to our entire set. There are k possible decisions to make for the first trade, because there are k trades. And there are 2 to the n possible decisions to make for how to split up the output set, because there are 2 to the n subsets, and you must always choose one subset and its opposite. This means that if we already have this lookup table for everything smaller than our output set, then this only takes k times 2 to the n time. And overall, there are at most I times 2 to the n entries in our table, because there are I items, and there are 2 to the n possible subsets that they could go out to. This means that if we can manage to do everything in the right order, we should be able to fill out our table, computing each entry only once, in only I times 2 to the n times k times 2 to the n time. And that's equal to I times k times 4 to the n. In all of our examples, n is very small, whereas k and I can be very large. So this is good for us, because this means that we are linear in the variables that can be large, and we are exponential, and the variable that we're exponential in is usually very small. So this should fit within our time frame. So what order do we fill this table out in so that we always have all the information we need? Well, we know that every set can only depend on its subsets. So if we fill it out so that we do all of the smaller sets first, and then build up to bigger sets, we'll always have the information that we need at each step. This should allow us to fill out the table computing each entry only once. All right, so now let's look at the code. First, we'll declare a couple types that will be useful to us later in the program. We'll have a type that can contain one trade offer, which will know the amount of time that it takes, the item that it needs, and the items that it puts out. We'll have an implementation of a linked list, so that we can iterate over sets that we've assembled in lists later. Then we need a bunch of functions for dealing with sets. We'll represent sets as bit masks, because those are easy to deal with in C. We'll represent a set as a long, that's 64 bits, which is larger than anything we'll ever encounter in this problem, and have a 1 in a position if it's in the set and a 0 in the position otherwise. So for instance, to get a set with a single element, all you have to do is raise 2 to the power of x. Or you can count the number of 1s in a bit mask to get the number of elements in a set. I guess here we have our method for destroying a linked list so that we don't run out of memory during the execution of our program. And then we have a method for getting all of the proper subsets of a set. We'll need this during our decision making on how to split up the output. And to do this, we count the number of elements in the subset. We find out how many subsets of that subset there will be. And then we iterate through all permutations of bits we could flip off and construct a list with those bits flipped off in each element. Now that we have those helper functions, we're ready to actually solve the problem. The first thing we should do is read in the input format. We read in the number of IDs, we read in the number of desired items. We go through that many next lines to read in each desired item. We read in the number of trades and then go through each successive line after that to read in that trade. And then we're done. Then before we actually start our computation, we need to initialize our table. So we'll have a table that says, how do I get to a specific output set that's going to be the first index from a specific item, and that's going to be the second index. There are Pn total output sets, that's 2 to the n, and NIDs possible items that you could put in. So this is the maximum size of our table. We'll initialize everything to -1 because all the costs are positive, so -1 will be a signal to us that we haven't computed this one yet, and or it's impossible. And then we'll do our base case for our DP, which is that we know that you can always get to a single element subset by starting with that element. So for instance, to get to the set 8 from the item 8, it costs 0. Then, before we start the DP, we're going to determine the dynamic programming order by generating a list of subsets of each size. So we'll just generate all the subsets, which is easy because you just count all the numbers between 0 and 2 to the n, and then count the number of bits that are on each of them and add it to the appropriate list. We'll need this list of subsets so that we can iterate over all the subsets of size 2 before we iterate over the subsets of size 3, etc. Now that we've set all this up, we're ready to start the dynamic programming. So first, we iterate over possible subset sizes, starting at 2 and going up to the entire set. So first we iterate over subsets of size 2, for instance. Then we iterate over subsets of that size. We assembled the list of subsets earlier, so we can just iterate over the linked list that we assembled then and get those subsets. Then we need to iterate over all possible subsets of that subset. And that's the decision of how to split up. And that's the decision of how to split up that output. So for instance, in this subset, we need to make this decision again. So we get the subset, and we get the inverse of it, which is the opposite that the other trade item needs to produce. And then we iterate over our trades to see which ones can produce those outputs and which ones are fastest. So once we have a trade, we determine whether it's possible to produce our desired output sets using it by seeing if we can make the selected subset using one of its outputs and its inverse using the other. This will mean that it can cover the entire desired output set. If we can, we'll determine how much it costs to do that. So we'll take the amount of time that it took to go from our one item to the entire output, and the amount of time it took to go from the other item to the entire output, which was A and B in our original example, and we'll add it to the cost of the first trade, and that's C in our original example. So then we get the total cost of this arrangement, A plus B plus C. Then we see if it's better than the best running minimum that we have so far. And if it is, then we update the running minimum so that at the end of the loop, we have the least possible cost to get from each possible input to this subset. This will go up the table, and will fill out all the entries that it possibly can until it has reached the subset that contains all the elements. Once we've filled out the whole table, we can find the answer simply by looking at the table, at how do you get to the entire set, which is Pn minus 1, the bit mask with all ones, from the item 0. We read off that cost and print it out. And this was trading up.